Sorry, you've obviously like signed up for the wrong class because we're not going to do a rock concert on the projector or anything. But this is much more interesting than a rock concert. We're going to do the maximum weight perfect matching problem. Or sorry, maximum weight matching and perfect matching. So bonus. So just to be clear, the idea is we've got an input, which is a graph G, and a weight function on the edges. So the weight of each edge is given by this function W. And then the goal is to find a matching with maximum weight. So matching M in G of maximum weight where the weight function we think of as being like linear, right? So maximize the sum over all edges in the matching of the weight of that edge. Okay. So this is asking, for any matching. And here I've got the weights are real, right? You could also have a similar problem where you could ask for the perfect matching of maximum weight. So here, just the goal would be you find a perfect matching of maximum weight. Okay. Perfect matching, right, just means every vertex gets saturated. So it hits every vertex. Very related problems, but they're not quite the same. But we're going to see that actually, in some cases you can reduce one to the other. Okay. So sometimes it's going to be useful to think of a matching in terms of an indicator vector. Okay, so I'll write this over here. So it's useful to think of a matching M in terms of its indicator vector. So what I mean by this is it's just, so maybe for some notation for this, I could say 1 subscript M. And this is just basically a vector where it says, okay, for each edge in the graph, it outputs a 1 if that edge is in the matching and a 0 otherwise. So I could say it's 1M UV, where UV is an edge of G, where this 1M UV equals 1 if E is in the matching and 0 otherwise. So this, so this is a vector where, vectors usually you think of first coordinate, coordinate 1, 2, 3 up to something. here we've got coordinates that are like, they're not indexed by numbers, they're indexed by edges of the graph. So every edge corresponds to a coordinate. So, so right, I mean, what is the maximum weight matching problem? Well, I mean, really, you could think of it as a numerical problem involving the indicator thing. So, right, so we're maximizing the sum over all UV in the edge set, the weight of UV times the indicator, you know, M evaluated at the edge UV, subject to subject to the fact that this has to be a matching, which means that, so yeah, I want to just think of the entries of this, well, yeah, let's actually change this a bit. So let's write this more in the way that we usually write a linear program. So let's change this to x. So x UV. So for each edge, let's say we have a variable x corresponding to that edge, x UV. And you can kind of think of this maximum weight matching problem as I'm maximizing, so this is the weight of that edge times the variable corresponding to that edge. And in a matching, what you would have is that for any vertex u, if I sum over all the neighbors, so all of the v in the neighborhood of u, of the variable corresponding to the edge uv, if this was really an indicator function of a matching, this would be at most 1. Okay, and also x uv would be at least 0 for all. So this is for all u in the vertex set, and this is for all uv in the edge set. Okay, so I guess what I'm trying to say is I'm sort of trying to take this maximum weight matching problem and turn it into like a numerical problem, right? I'm just, I take a variable for every edge. This is my condition that it has to be a matching, that, you know, from every vertex there's at most one matching edge. And obviously the each variable has to be non-zero or non-negative. So any indicator function of a matching would satisfy these two conditions, right? Okay, so this is a linear program, right? I'm maximizing some linear function of some variables subject to some linear constraints. Now, here's the thing. I mean, this actually is not going to solve the maximum weight perfect matching, or the maximum weight matching problem. Oh, and by the way, if I wanted to make it a perfect matching, you just make this a 1, right? Equal to 1 instead of less than or equal to 1. So yeah. But this gives us a linear programming approach to a matching problem, right? We can write this linear program. We can see what it gives you, right? But this may not actually solve the problem. Can anyone see like why this? So if I solve this linear program, it may not actually solve the maximum weight matching problem. So I'm not necessarily asking for like a counterexample or something, but just a rough idea, like why is this not the same thing as the maximum weight matching problem? Well, so these, so if I want to find an actual matching, the indicator vector of the matching all of the values will be equal to 0 or equal to 1. If I'm treating this as a linear program, it might output fractional values, right? The actual maximum may be attained at some vector or at some point where the variables are fractional values. So, but this gives you an upper bound anyway. So so the value of this LP is at least the answer to the maximum weight matching problem. And if you were lucky and all the variables ended up being 0 or 1, well, then you would have actually solved the problem. But you might not be that lucky. In fact, it's not hard to come up with a counterexample. So let's just say you take a 5 cycle as your graph. And let's say that every edge has weight 1. Then in this linear program, what is it? So it's trying to if every edge has weight 1, just trying to maximize. I've got 5 variables, 1 for each edge. And it's trying to maximize the sum of those 5 variables. I've got a condition at every vertex, the weight of that edge plus the weight of that edge has to be at most 1. That's what this condition is saying. That, yeah, around every vertex, the edges have to have weight adding up to at most 1. And all the weights have to, all the variable kind of values have to be at least 0. So I could do something like half everywhere. So let's say my x variables, I just assign a half to every edge. Right? This is going to satisfy the constraints, and this gives me like a matching with 2.5 edges. So this has like value. So the value of this LP is going to be at least 5/2. Okay, but if I actually wanted to find the biggest matching in this graph, it's going to have 2 edges, right? I can't take more than 2. I could take this edge and then maybe this one. But if you think about it, you won't be able to take a matching with more than 2 edges, right? It would have to be 3. But this linear program gives kind of the wrong value. Any questions about that? Okay. So basically, I've been leading you in the wrong direction, right? We started by trying to solve the maximum weight. Okay, this is an approach, right? This gives you an upper bound on this maximum weight matching problem. It's the wrong number sometimes, but here's the magical thing, that it's also the right number sometimes. So let me explain. So let's say a fractional matching in a graph is a vector say xuv, where uv is an edge of G, such that, so basically it satisfies the constraints of that LP. So the sum over all vertices in the neighborhood of U of xuv is at most 1 for all vertices in the graph. And all of the variables are at least 0. So what we saw in that example is an example of a fractional matching that can't really be represented using actual matchings. because we had like a matching of weight 2.5, but the graph over there only has a matching number equal to 2. So here's the kind of a magical thing, which you're going to prove on assignment 3. It's a very standard thing, so yeah, it is doable. So in a bipartite graph, every fractional matching is actually a convex combination of indicator functions or indicator vectors of matchings. So if you have any fractional matching in a bipartite graph, you can actually express it as a convex combination of indicator functions of actual matchings, where the values are 0 or 1. When I say convex combination, I mean like, the vector x. Let's say this fractional matching is called x. We can express it as sum of lambda I, indicator function of mi, I equals 1 to k or something, where the lambdas add up to 1. So that's what I mean by like a convex combination. But this is actually brilliant because this means that, so yeah, apologies for not proving this, but you're going to prove it, that this can be done. But the magic thing about this is that this means that for a bipartite graph, this linear program gives you the right answer. So a corollary of this is that in a bipartite graph, the kind of linear programming, so this linear program over here, we can call it like so it's an LP relaxation of the maximum weight matching problem. What I mean by that is it's basically it's the same problem, except that it's allowing the variables to be fractional, right? So that's what I mean by an LP relaxation. It's a linear program which is basically solving the problem, except that it's allowing the variables to be rational, whereas in the original problem they shouldn't have been rational, right? They should be integer. So in a bipartite graph, the LP relaxation correctly solves the max weight matching problem. So maybe I'll ask you guys, do you see why this lemma implies that? No? Kind of. Some people may be thinking about it. Well, here's the idea. Okay, we know that the LP relaxation gives an upper bound. Like the maximum of the relaxation could be higher or whatever, right? But anyway, take a solution, take the optimal vector for the LP relaxation. It is a fractional matching because it satisfies the constraints, because those are the same constraints as here. Okay, so that's like it's a fractional matching. It might give some non-integer values somewhere. Take that fractional matching and write it like this, where these are actual matchings. And these things sum up to 1. And these are all x lambda 1 up, So sorry, these are also non-negative numbers, right? That's what a convex combination means. So take your optimum thing from the linear program, write it like this, and then let's think about it. Take one of these matchings. Could that matching have smaller weight than my fractional matching? If even one of these, so I guess what I'm saying is just take any of these things, and I claim that all of them are just as good as X is for the LP. Like they all give the same weight as X, because how couldn't they, right? Suppose one of them had a smaller weight. I guess what I'm saying is like, basically like the weight of X, meaning like that sum over there in the maximization thing is the sum over lambda I, the weight of mi. If one of these had weight bigger than the weight of X, that would have actually been the solution to the linear program, so you should have taken that instead, right? X is optimal for the linear program. If any of these are smaller, then how could I add up a bunch of numbers that add up to 1 with something smaller? Like, you're not going to be able to get this value, right? So yeah, it turns out that basically solve the linear programming thing. You can express the fractional matching in terms of actual matchings, and since the weight of mi is at most the weight of X, because X was optimal for the linear program for all I, it must actually be the case, and the lambda i's sum to 1, it must be equal. So yeah, solve the LP, find an expression of X in terms of these things, and then take any matching in that expression, and that's going to also be an optimal matching. Okay. Yeah.
Sorry, is the M1, are they changing? Like X, like we're iterating through I decay of the lambdas.
Yeah, this should say MI. Yeah, sorry. The I was kind of like not very clear, yeah. So like the problem with non-bipartite graphs is that you could have a fractional matching like this one, and this just cannot be written as a convex combination of actual matchings, because one of those matchings would have to have at least 3 edges. You can't have a 3-edge matching in this graph, right? Because yeah, the kind of overall weight here is bigger than 2, so you couldn't just make this using 2 edges, right? So, okay. But so this actually gives us an approach for this maximum weight matching problem in bipartite graphs. Like, we know that linear programs can be solved in polynomial time. If you wanted to solve this problem, just write down the linear program, which only has polynomial size in terms of the graph, and then solve it. Okay. So therefore, basically, this maximum weight matching problem in bipartite graphs can be reduced to a linear program. But we're going to also do it in another way as well. Actually, if we think about duality, this gives us something kind of interesting, right? Because if that linear program solves the maximum weight matching problem, then so does its dual. Because by strong duality, the value of the linear program is equal to the value of the dual. So we can also take the dual of that thing. Okay. And conveniently, that linear program is already in standard inequality form. Okay, so yeah, the dual linear program, like for that one over there. So original linear program is maximizing, so I must be minimizing. Well, let's say, so I want to write this in terms of a function on the vertices. So yeah. Over here we have one variable for every edge and one constraint for every vertex. And then we have non-negativity constraints. So like the number of variables is equal to the number of edges, number of constraints equals number of vertices. So in the dual, you should have one variable for every vertex, one constraint for every edge. So I'm going to represent my variables with a function. So f is a function on the vertices. The fact that I'm mapping to non-negative reals is because the constraint in the dual. And what we'd be doing is minimizing. It turns out it's the sum overall f of v, where v is a vertex. The reason is because in all of these constraints, the right-hand side is a 1. So what I'm taking is like the all ones vector dot product with my variables. Because, yeah, basically, like, maybe I should write this duality thing again, right? If I'm so if you've already kind of memorized this by now, then you don't need to write it again. But in case it helps, right? So if that's my primal LP, that's the dual. So yeah, in my primal LP over there, the B vector was just ones. And so now my objective function is just like the all ones vector times my variables. So that's this. And subject to what it turns out is we're going to want f of u plus f of v is at least the weight of uv for all uv in the edge set of G. And okay, I guess I've got this condition. Okay, I guess I kind of wrote it up there, but anyway, I can also write it again. Okay. Right, because the coefficients in the objective function of your primal should become the constraints. Like it should be over here in the dual. And that's why over there you had the WUV in the primal, and now in the objective function, and then in the dual you've got it as a constraint, right? It's not quite. It's actually what do you call it? Incidence matrix. So. But that's actually good to think about. Like my A thing would be, so over there I had one one constraint per vertex. So you've got a row for every vertex of G. You've got a column for every edge of G. And then if I've got like an edge E, which is UV, let's say, then like in this row, everything's 0 except the column corresponding to U would get a 1, and the column corresponding to V would get a 1. So yeah, this is usually called like the incidence matrix of the graph. Okay. Yeah, so when I take the transpose of this, I've got just two ones in each. So here it's each column, but in the transpose is each row, and that corresponds to the two things here, the two ones. Okay. So yeah, the linear program in a bipartite graph is going to solve the maximum weight matching problem. So the dual solves the same problem, right? By strong duality, they give the same answer. So this actually leads us to a theorem. So this is called Egger-Varese theorem. So in a bipartite graph, the maximum weight of a matching is equal to the minimum of, so the sum over all vertices of the graph of f of v over all functions f from the vertices to the non-negative reals, where f of u plus f of v is at least the weight of the edge uv for all uv in the edge set. All I'm writing here is that this dual linear program solves the same thing as the primal, and we know that the primal correctly solves the maximum weight matching problem in a bipartite graph only, right? But okay. Remember what we did last time, like Koenig's theorem? So that wasn't about weighted matchings. That's just trying to find the biggest matching. So in Koenig's theorem, we said the biggest matching in a graph is equal to the cardinality of the smallest vertex cover. Do you see any like connection here? Like, suppose I put the weight of every edge as being 1. Then if you think about it, if I took the f to be an indicator function of a vertex cover is a set of vertices that hits every edge at least once. Then for every edge, if the weight of the edge is 1, you would have that f of u plus f of v is at least 1, because every edge gets hit by a vertex cover. So in some sense, this is like this is kind of a weighted version of Koenig's theorem in some sense. This doesn't quite imply Koenig's theorem, though, right? Because in Koenig's theorem, you can always find this is kind of a fractional vertex cover. There's no guarantee that these numbers are going to be integers, that they're going to be 0 or 1. But in Koenig's theorem, they're actually equal to 0 or 1. Does that make sense? Okay. So yeah, the proof of this theorem is just by the corollary that we wrote down before, and strong duality. So yeah, by this corollary. Plus strong duality for linear programs. Okay. Any questions about any of this? Okay. Okay, this is great. I love that you can reduce this down to a problem in linear programming. It shows this connection from one problem to another. But like, we never talked about how to actually solve a linear program in polynomial time. So I think it's actually useful to, instead of just, so we could rely on linear programming to solve this in polynomial time, but we can actually just do it directly. So that's what I'm going to focus on now. How do I actually take a maximum weight matching problem in a bipartite graph and actually solve it, like by hand, without linear programming? But it's worth knowing that you can just write down the linear program. So if you have access to like an LP solver or something, just write the linear program and send it off, right? Unless you wanted to do it somehow more efficiently. So okay. So yeah, now I want to actually solve it. So we're going to give a combinatorial algorithm. I don't exactly know what, so maybe I'll put this in quotes because so for the max weight matching problem. I don't know if there's a good definition of what a combinatorial algorithm is. It's just like, if it feels like you're doing something combinatorial, you're like walking around paths in the graph and doing combinatorial stuff, then that's a combinatorial algorithm. I mean, in some sense though, like if you're in the doing linear program, the simplex method is like kind of combinatorial as well. But anyway, but this will be more efficient than something like the simplex method. Okay, so this is something called the, it's usually called the Hungarian algorithm. Okay. Actually, before we give this algorithm, it's going to be convenient to actually take any maximum weight matching problem and first turn it into a perfect matching problem. Because it's going to be convenient for how we describe the algorithm. So yeah, so let's let G be a bipartite graph. So I'm going to do a few reductions first. Let's say with bipartition xy. So I claim that as a first step, we can assume that the size of x is equal to the size of y. Okay. And this is actually for fairly stupid reasons because, I mean, if they weren't equal, like let's say x is way bigger than y, and there's some edges here and whatnot. Well, okay, I mean, I could just add more vertices. Now I make them the same size. So that's literally all you do. So, right, so if y is less than x, let's say, add x minus y edges or vertices. To y. Okay. Let me make another sort of observation. So if I'm solving the maximum weight matching problem, I can assume there are no negative edges. So we can assume no edges have negative weight. Any thoughts about like why that's legit? Like why I can do that? Yeah.
We're just trying to maximize the weight. We can just maximize the, if there's a negative weight, we can just maximize the weight function plus whatever to make it positive.
That's often a good approach. Although in this case, it's not necessarily going to work because so let's say all the edges were -1 or something, right? Let's say I add 1 to everything, or let's say I add 2 to everything to make it positive. So every edge has weight 1. And let's say there's a perfect matching, so I would take it, and that would be my maximum weight matching. But actually, if all the weights really were -1, my maximum weight matching would be don't take any edges. So, and that actually kind of hints at why, I mean, because, so if you were doing like a perfect matching problem, that would be a different story if you're forcing them to take a certain number of edges. But if I allow myself to not take any edges, you know, if there was an edge of negative weight, like could the best matching have that edge? No, because you would just take it out and you'd still be a matching, and it would just go higher, right? So, so this is just because. So yeah, we can just delete. Well, you know, no max weight matching would ever contain a negative weight edge. So no max weight matching would contain one. So just delete them from the graph and then solve the problem for the new instance. But the approach you're saying works in a lot of problems, so yeah. Third reduction, I'm going to make, well, we can assume that between x and y, every single edge is there. So we can assume G contains every possible edge from x to y, meaning that it is it's a complete bipartite graph. Any idea like why I can assume that? Like what I would do? Suppose it didn't, right? Suppose some edge is missing. exactly, yeah. Put it in, give it a weight 0. At the end, if you find your matching, if it's in the matching, well, just take it out. It doesn't make a difference. Yeah. And vice versa, take the biggest matching in the original thing. And if you could add that edge, put it in or don't, or it really doesn't matter. So yeah. Yeah. So basically the idea is just give any such edge weight 0. So if it's missing, put it in and just give it a weight of 0. Okay. So actually what we're doing now is we're solving the maximum weight perfect matching problem in a balanced, complete bipartite graph. Balanced meaning the sets are the same size. Sets are the same size. It's a complete bipartite graph. And yeah, we're trying to find, you may as well find a maximum perfect matching, because if it wasn't a perfect matching, you could pick any pair, any vertex in X and any vertex in Y that's not matched, match them up. It might give it a 0, or it might give it something positive, and it always gets better. Okay, so so actually this thing about negative weight edges was useful to reduce it to this problem, but now now we're going to solve the maximum weight perfect matching problem, and I'm going to re-allow negative edges again. Yeah?
Does reduction 3 mean that instead of reduction 2, could you just set every negative weight edge to 0?
Yeah.
Instead?
Essentially, that's what by deleting them and then doing this, I am kind of doing that, yeah. So you could have done it at that step and then add in the missing edges, yeah. But that works, yeah. Okay. So basically, solving the maximum weight perfect matching problem under the constraint, under the addition non-negative, is the same thing as solving the maximum weight matching problem. But that doesn't, so now I want to solve a more general problem. I'm going to allow the edges to be negative, and that's going to solve a more general case. Okay, so what we're actually going to do is the maximum weight perfect matching problem, and that'll solve the maximum weight matching problem. So, yeah. Maybe I want to write the algorithm over here. There's more space. So basically, our input is a bipartite graph G. Well, actually, it's a balanced, complete. Balanced means X and Y have the same size. Complete bipartite graph G, and a weight function W, and I'm going to allow negative edges. So every edge just maps to the reals. Okay. Okay, and our goal is to find a maximum weight perfect matching. Although when I say this, like that was mentioned earlier about just adding something to all the edges, that would work here, because if I add 100 to every edge, I find a maximally perfect matching. I then subtract 100 times, number of vertices over 2 or whatever is this extra amount I've got, then it'll solve the original problem. So you could assume all the edges are positive if you wanted to. Anyway, so throughout the algorithm, we will kind of so at every step, so we will have a function f from the vertices to the reals. So this, we're going to initialize this function at the beginning, and this function is going to kind of keep track of some stuff for us with the property well, it's basically the property from Egger-Vari's theorem that the sum of the f values on the endpoints of an edge, so f of u plus f of v, is at least w, the weight of uv, for all edges. Okay. So basically, we're going to start out with this function having very high values, and then we're going to kind of try to push it down, sort of, but while maintaining this condition. So we always want this to be satisfied at every point, but we're going to try to push this function f down. Okay, so this is called we're going to call this a feasible function. Okay. The word feasible here is coming from the fact that this function will represent a feasible point for the dual linear program. There is one difference here. In Egger-Vari's theorem, this was a function mapping only to non-negative numbers. But since now we're solving the perfect matching problem, okay, there's something on your second assignment so the perfect matching problem, right, it's in standard equality form because you have equality constraints. It turns out when you take the dual of one of those, it gives you something very similar to the dual of in standard inequality form, except you lose the non-negativity constraint. So it just gives you a constraint that it's a real number. It does with no non-negativity. So anyway, this is going to represent a feasible function for the dual. Okay, so we're going to keep these functions and an edge uv we'll say is tight for f if you actually get equality here. So if f of u plus f of v equals wuv. Okay, and then we're going to so at every step, the graph of all tight edges will be denoted h sub f. Okay, so if I gave you an f, you could just check all the edges, check if they're tight, and then that would be how you construct this graph. And at every point, M will be a matching in H of F, H sub F. Okay. So this is going to be kind of an interesting algorithm. Basically, the function f you should think of as it's a feasible point of the dual of the linear program, and m is a matching, so it's like it's a feasible point of the primal. And basically, we're going to kind of try to push these things closer to each other, right? We're going to take the f and try to like kind of decrease it while keeping it feasible, and the matching m, we're going to try to increase it. And like once they meet, then you know that you've got the answer, because now the primal equals the dual. Okay. So initially, actually, oh yeah, maybe let me say something which is kind of a key point here. If we ever get a perfect matching m, if m is perfect, then we win. Let me say what I mean by that. So here's a claim. If f is a feasible function, and m is a perfect matching in the graph of all the tight edges. So by the way, this h of f has all the vertices of G, and it just has an edge. Like the edges are the ones that are tight. So if f is a feasible function and m is a perfect matching in HF, then m is a max weight perfect matching. So basically our whole goal is like try to get a perfect matching in the set of tight edges, in the graph of tight edges. And if you can find one, it is the best one. It's the best possible matching. Okay. The proof is fairly easy. It's like, well, if I sum over all the UV in M of the weight of UV, I know that all of the edges in M are tight. So I can just replace this by f of u plus f of v. Because the edges in M are all tight, because M is a matching in HF. And it's a perfect matching in H of F. So every vertex of the whole graph appears as the endpoint of exactly one edge of M. So it's either, every vertex is either f of u or f of v exactly once. So this is just equal to the sum over all v in the vertex set of f of v, because it's a perfect matching. And any other perfect matching M prime would just satisfy the same thing, but the first one's going to be an inequality, right? So it'll just be like because if it's a perfect matching, you still have this equals that, but this will be at most that because it's a feasible labeling and the edges are not necessarily tight. So yeah. So if you get a perfect matching in H sub f, then you win. Any questions about that? Okay. All right, so let's describe how the algorithm works. So I have to tell you what f is at the beginning. And like I said, at the beginning, I'm just going to let the f of v be a large number for every vertex v so that it's definitely feasible. So set f of v to be like the maximum of all the weights or something over all the edges. And maybe I'm a bit worried about negative numbers, so let's also put union 0. But because if like all the edges are, I don't know. Anyway, just make it bigger than it needs to be. For all vertices. And then I think it's pretty clear that I think like h of f will just be the graph with the vertices of G, and it's going to have an empty set of edges because I don't think, well, maybe something could be tight. I don't know. But h of f is just now, it's the set of, is the graph of tight edges. You could compute that from f. I guess in theory, if like every edge had weight 0, now everything is tight, and maybe, yeah, anyway. And then initially, M is going to be the empty set. Okay, now I need to tell you how to update this situation. Okay. Okay. But yeah, it's clear how you would initiate it. Just put big numbers on the vertices. Compute your tight edges. There might not be any, and then M is the empty set. Okay, so I want to make M a perfect matching in HF, then I win, right? So while there exists, well, while M is not perfect, do the following. So first, if it's not perfect, then there's X and Y have the same size, right? So if something's unsaturated somewhere, then there's something in X that's not saturated. So let U be an element of X that's not saturated. Okay. So what I want to do is try to find an augmenting path. If I can find an augmenting path in HF, then I could replace M by a larger matching by following along that augmenting path. So now I'm going to construct, this is quite similar to the proof of Koenig's theorem, the set W of vertices that can be reached from U by an M alternating path in the graph HF. Okay. Now, during that process, if you add a vertex from Y that's not saturated, if you add that to W at any point, so if at any point you encounter, I guess, I mean, like, if you add something to W, so you add some unsaturated Y in Y to W, then you actually found an augmenting path. So, so augment M along a path from U to Y. Okay. And that'll give me a bigger matching. And then I'm going to, so step 3, I'm going to write in a second, but if this happens, then we skip step 3. So I haven't written step 3 yet, but if you managed to find an augmenting path, increase the matching, and just go back, skip step 3, basically. Because what we're trying to do is get this matching as big as we can. If it's perfect, we just win, right? We output it. Okay, of course, you may not be able to get a bigger matching. So if W does not contain an unsaturated vertex of Y, okay, then we do the following. So basically what I want to do now is, so I'm not going to be able to get my matching bigger at this point. What I want to do is take this feasible function and kind of push it downwards, like decrease the values somehow. So specifically what I'm going to do is I define some number alpha, which is the minimum overall x and W intersect, or x intersect W, and all y in Y take away W of f of U plus f of V minus the weight of UV. Okay. So this is just some number. Oh, sorry. This U and V should be X and Y. Okay. And update the function f by setting, like, f of v, we're going to make it equal to f of v minus alpha if v is in x intersect w. It's going to be f of v plus alpha if v is in y intersect w. And then it's just equal to f of v, so it doesn't change otherwise. Okay. So maybe I'll just keep writing this. I'm almost done explaining the algorithm, and then we'll analyze it in a second. And then at the end of this, once I've done this update to the function f, instead of going to the next step, I'm going to go back to step 2. And I'm going to keep trying to build this set W and keep trying to reach an unsaturated vertex of Y. So go back to step 2. Okay. And then, step 4, So if I actually, yeah, is just says if M is perfect, output it. Because if it's a perfect matching in HF, then that's good. Okay. Okay. So let's kind of try to argue to ourselves that this is going to work. So I think everything in like step 1 and step 2 and step 4 is kind of clear. Like, I mean, in step 2, if you find an augmenting path, augment it, and then you get a bigger matching. Step 4, if you find a perfect matching, you're happy. I mean, step 1, you can always do that. I think step 3 is like the weird one that we need to think about. And like we kind of need to think about, why is this not going to just loop on forever or something? So, so here's one thing to note. So in step 3, so I claim that the alpha is well defined. Like I'm not taking the minimum over the empty set or something. Well, I guess that might be well defined anyway, but and positive. Okay. So here's the reason. So when I'm building these alternating paths, right? I start at U and I take all the possible neighbors of U, right? Each of these could be, yeah, this path of length 1 is an alternating path. Because, yeah, this guy's, and if any of these were unsaturated, I would just say, I found my unsaturated vertex in Y, and I'm done. So what actually happens is that since we're in step 3, what we know is that each of these must be matched to someone. Okay. But then we could, of course, take the neighbors of these guys, but all of them must be matched to someone. And we could just keep going back and forth like this. And if you think about it, the number of things here, so the number of things in X intersect W will always be bigger than the things in Y intersect W, because everyone in Y intersect W is matched to someone in X intersect W, but also U is in X intersect W and isn't matched to anyone. Right. So this set's bigger than that one. That means this set's not empty, because it's bigger than something. So so X intersect W is not empty. But also Y take away W is not empty, because X and Y have the same size. And this set has size less than X because it has size less than X intersect W. So because Y intersect W has size less than X intersect W, which is at most size of X, which is equal to the size of Y. So there is some, so this set is non-empty, and this set is non-empty. So you can actually compute this. There is some X and some Y. And I also claim that the edges from x intersect w, so this is x intersect w and y intersect w, and then I've got like y take away w. So I claim that these edges are not, there are no tight edges here. Because if there was, I could follow along a path from u, and every second edge in that path is a matching edge to that vertex. But then this would give me a longer alternating path that ends in this set, right? So there are no edges. There are no tight edges. From x intersect w to y take away w. So therefore, this number is positive because there's always a gap between this number and this number because none of these are tight. Okay. But now the idea is, by doing this update, we're decreasing everything in x intersect w by alpha, and we're increasing everything. So everything in this set goes down by alpha. Everything in this set goes up by alpha. That means anything that was tight here is still tight because the two endpoints just went up and down. And also, it's still going to be feasible. And everything here just stayed the same. Like it's like plus 0. Everything here stayed the same. But one of these edges, the one that had the minimum gap between the thing, like that where alpha was defined, that one's now going to be tight. So one edge that wasn't tight before, we've decreased this by alpha, and that edge became tight. So that means if we go back to step 2, then all of the tight edges we had here before, they're still tight. Oh yeah, you have to check also this stays feasible, but it does. All the edges here we had were tight before are still tight. I have one additional tight edge here. And what that tells me is that actually my W, if I restarted that process, I would get a larger set W. So now keep doing that. So every time I go back to step 2, the set W increases in size. Until at some point, it must reach an unsaturated vertex of Y. It can't keep increasing forever and never reach an unsaturated vertex because I've only got finitely many vertices. And at that point, you augment the matching. Then you skip step 3, you go to step 4. And then you do this loop over again. So yeah, I think we are out of time, but that's the idea. So this will always stay feasible, and you'll keep basically applying step 2, making the set W bigger and bigger. Keep changing your F function on step 3, and if this set eventually this set's going to have to incorporate an unsaturated vertex, and then you've got your augmenting path, and you win, and you go to the next step. All right, so yeah, see you guys on Thursday.